Okay, great. Well, thank you everyone for having me and for being here. I do receive research funding from the Olympus Corporation, but that'll have no bearing on the talk today. So we're just going to start with a general outline, and the entire purpose of this is not to make it so you're able to do AI as soon as you leave this room, or machine learning, or any of that, but just to know what these terms are, because unfortunately they're often conflated and mixed up with each other. And just having a little bit of clarity, so you know when people are actually mentioning like, oh, I did like an AI paper, you're like, oh, actually, so you're able to kind of look at things and access things critically. So we'll start with what is artificial intelligence. So AI is the field of study, and its entire purpose is to make computers function intelligently. So then that begs the question, what does it mean to be intelligent, as my wife often asks me. So first it is to understand, process, and then act. I like to refer to this as UPA. Just in order to as a mnemonic, but we can go through some examples here. So this is at the bottom of the hill where I live right here, and this is just, as everyone knows, a traffic light. And there's 3 different colors on it, 3 different lights, and you can see that it's a red light. And we as humans can understand this and say, especially those who drive and get around, knowing that this means that you should stop when you get to an intersection. So not only are you seeing this metal structure that has red light, but you're understanding what its signal and what it's trying to convey and mean. Now, if you take 20 yards going back, looking out at the Boston Common there, you'll now see a red light that's in an intersection. And so this is the process. So not only now do you recognize this is a red light, I know it means to stop, now you're an actor, you're a bike, you're a pedestrian, you're a car. And unlike most Boston drivers, hopefully you'll see red light and say, I should probably stop at this intersection right here. And then last is acting in the world. So now you've understood, you've processed what this red light means, you're at the intersection, and then you'll put on the brake. And so we have some applications of this done by computers in real time, even today with autonomous vehicles. And you'll see some of this in the Tesla, for example, where it's able to recognize this light and actually enact this through no interaction with the driver, he or herself. So next up is machine learning. So we've covered AI, UPA. So what's machine learning? Because often these things are flipped around. So it's a field that tries to teach computers and machines how to learn, which again, they went to say, what does it mean to learn and how can you learn? So the first kind of learning is supervised learning, and we do this all at home, and we did this in elementary school, middle school, high school, up through med school, and hopefully still today somewhat. And it's where you get examples on flashcards, and through these examples it says, this is a dog, and then it shows you a picture of a dog. And we actually are able to do this in surgery right now. So if you give the computer pictures, for example, of the gallbladder and label it and say, this photo, it has a gallbladder in it, it's able to extract these images, make sense of it, and then when you show it again, as in the bottom right of this image, it will say that, yes, this is a gallbladder, or in that bottom image, which is just the gastric specimen after a sleeve, it'll say, no, this is not a gallbladder because I did my flashcards, so I know what this is. This is in direct contrast to unsupervised learning, which is clustering. So these are just a bunch of star clusters here as kind of a learning feature. But through unsupervised learning, you don't get any labels for the computer. You give it a bunch of data and you say, figure something out and choose groups in here that are similar to each other. So again, going back with the gallbladder example, you'll see here kind of in the left side of the screen, there's 4 different cases, all of different views of the gallbladder. You give that to the computer through the algorithm. It clusters them in things that are visually similar. And it's able to kind of pick out the ones that don't have bleeding, the ones that do have bleeding. It doesn't know what bleeding is. It has no concept of that. But in this visual feature, it's very, very red, which is in contrast to the 3 images that are above. And then the last kind of main group of learning is reinforcement learning. As this is operant conditioning. You don't teach it what things are. Instead, you give it punishments or rewards, carrots and sticks, based off at what it does. And so it's able to make decisions saying like, oh, let me pull this lever like this mouse. If there's a green light going, it gets a reward. But if there's a red light, it gets a shock. And so you don't teach it that green is good and red is bad. Instead, what you reward it with the outcomes or you punish it. And it says, I'm not going to do that again because I got hurt last time. So it's just like a child with an iron, knowing not to touch it. Now, we know the 3 types of learning, which is, supervised, unsupervised, and reinforcement, but how do you actually make the machines do this learning? And that's all through different mathematical models as underlying all of these things. So you'll see tree-based, which is becoming more and more popular as we have more computing power, either through normal random forest or more recent gradient-boosted trees like XGBoost or LightGBM. Even regression, though, is learning, right? You're teaching a computer, given these set of variables, predict for me what the outcome is. That's what we call our regression variables predictors. There's also clustering and hierarchical clustering that you can use in addition to k-nearest neighbors, and then deep learning. And we'll focus on the deep learning part because of the fact that this is what's really led to some big advancements over the past 10, 20 years. In particular, these multiple layers of artificial neural networks. And what that means is you just have neurons that are on or off, just like in your brain, and you structure them through multiple layers and different connections. And through this, you're able to, through infinite combinations, really represent very complex functions, just like how we work. So big picture, this is the thing that you kind of want to sear into your brain now, is you have these concentric circles that are overlapping this Venn diagram where you have artificial intelligence, where we're trying to understand how to get computers to understand, process, and act in the world. And in order to do that, they need to learn. And so how do they do it? They use machine learning, because that's how we teach computers how to learn and be able to have intelligence. And in particular, the type of machine learning, the models that have been very helpful have been deep learning models where you have those multiple layers of artificial neural networks. Now, this doesn't mean that AI is all machine learning. Some parts of it, for example, if you think about the ACT component, there's a very large field of study, which is just in terms of computer and human interactions with the world. There's other parts that are more philosophical, like what does it mean to understand? What does it mean to actually be intelligent? In addition to areas that study symbolic logic, for example. And so the AI field is actually quite large. And it's been around now since the 1950s. There's been lots and lots of study on it. So it's not exclusively built on what are neural networks and how to get computers to do the OOPA. Now we'll talk about computer vision, which is kind of a favorite of mine, what we study here at SAIL at MGH. And that's a subfield of artificial intelligence that tries to teach computers not only to be able to see and understand there's pixels coming at it, but to understand what is in the images. Now, computer vision's been around for a while. There was actually an MIT professor who was tasked with kind of solving, so the legend goes, of solving the issue of computer vision over a summer study project. Which obviously didn't happen. And so up until the kind of in the pre-modern era, what was it good for? What was it good for kind of being helpful to the post office? It could recognize numbers, recognize letters, and work with that. Now, what's kind of surprising and shocking with a lot of this is pre-modern isn't really when you would think it would be. It was before 2012. So we're talking about less than a decade now of where we've had human kind of level of computer vision and understanding of images. And what caused this to happen? What really occurred in 2012? Krzyzewski, when he published AlexNet, a group out of Canada, they used convolutional neural networks, which again are not new. They've been around since the late 80s and early 90s. And again, it's just layers of neurons that are on or off. But kind of the beauty behind convolutional neural networks is instead of taking an entire image where you have thousands upon millions of pixels and trying to understand from that, they're able to kind of take it down and condense just portions of it, small boxes of it, into things that are recognizable. So edges, textures, patterns of color. And then based off of those edges, textures, patterns of color, et cetera, that it finds, it's able to classify the image. Now, why couldn't we use this to any effect? They did use it actually for numbers back then, but we didn't have the computer power. And so if anyone here is into video gaming, the card on the right is a very powerful graphics card. Now, it's great for video games and displaying great high-definition graphics, but also it's fantastic at doing one thing and one thing very, very well, and that's large quantities of linear algebra. So just multiplication and addition on large multi-dimensional scales. And now that we have the power to do it, in addition to the networks, we've been able to have some pretty good success with everything. So we've given computers that visual cortex, just like we have. And so this is actually an image out of the paper. If you see on the top row, those are things that the machine classified as correct. So mite, container ship, scooter, leopard. On the bottom are what it was deemed incorrect and what it said the labels were wrong. And if you look at them, actually, I think many of us in our room would also be considered wrong compared to these labels. Especially this one in the bottom left here, which is supposed to be a grill of a car. Yes, that's in there. So is a light, so is a tree, so is the sky. But I think most of us would pick up on the fact this is a convertible. So we're not failing to be able to recognize objects. What we're failing really is just having our data inputs, which is kind of just a pervasive problem in all of AI and kind of beyond the scope of today. But the key takeaway point here is we're able to kind of use with computers and see just like humans can. And we've been able to apply this in surgery. I won't go into too much depth here because we're going to have some great talks a little bit later in this session. But for here, for example, this is a laparoscopic gastrectomy, which is a big case, lots of different views, and you have lots of different instruments. And this was a completely off-the-shelf algorithm that they just gave labeled data to and immediately got human-like ability to recognize a vast variety of instruments. We'll see this recently in a paper published by Dr. Madani, who's giving a session, I think, concurrently right now, on this is the go, no-go zone, where they had experts from across the world label laparoscopic cholecystectomy and say, where should you dissect and where should you not dissect? And the computer's able to very nicely recognize zones where we suggest that you suggest in here, and we suggest you say very far away from here. And then lastly, Pietro Mascagni out of ERCAD in Europe now was able to also do this with surgical anatomy. So teaching the computer, where's the gallbladder? What are two cystic structures entering into the gallbladder? What does it mean to have cleared off the lower third of the hepatic plate and actually recognize this critical view of safety and do it very, very well? Now, vision is good, but if anyone, especially if you're a med student or if you pop into a case 2 hours in, you'll know that it takes you a little bit of time to get oriented to what's actually going on in the field. So these computers are great at, you give it a single image and you can say what's in it, but we know that even from our human experience, that's not enough. And why is it not enough? This is a kind of a process diagram from a lap chole that Dr. Hashimoto put out a few years ago, where you'll see the steps of the operation up here at the top, and there's all these diversion steps that happen, taking into account things that have been going on in the past and kind of the current condition of the patient. So what we need is memory. And you'll see this here. This is the exact same case on 2 different phases of the operation, where at the very beginning of the case, you release the gallbladder peritoneum to free up the gallbladder. At the end of the case, you pull it off the liver. Now, you see the same tool, the same gallbladder is doing the exact same motion, hooking the peritoneum, and there's the liver there. So these are very similar images, and the computer's gonna get mixed up on these. And you honestly can't blame it, right? Like, for example, in this one, this could be somebody doing just a very nice lower 1/3 dissection off the cystic plate for the gallbladder, and you could still have the cystic structures connected over here. But how do we know that it's removing the gallbladder from the liver bed? We know because we watched the previous 20 minutes of the operation and saw that the tubular structures were clipped and divided from the gallbladder. And so that gives us the sense that we need to have time information. So what we need is a kind of a memory cortex that we as humans have. This is our hippocampus right here. And so how can we do this? We can do it through another kind of artificial neural network called an LSTM. This has seen a lot of success in natural language processing because you need memory in order to predict what the next word will be. If, for example, you read, Thomas did this, the next sentence you said he, just to be able to refer back to me. And so you have a sense of what came before. So you need this memory. You don't need to understand what's going on in this, but it's one of the units. On the bottom is kind of what's the current running thing, and then on the top is the memory. So every single time the current running thing goes in and it updates the memory. And how this looks then is we stack these 2 networks together. And so this was a paper where we showed that we were able to recognize phases in poem. What you have is these images through all these different times. You give it the image and you feed it to the visual cortex, the convolutional neural network. It says, okay, I think it's one of these things and ranks them. And then you feed it to the memory, which then has learned the structure of the operation. It says, actually, previously you did this step already, so I know it can't be step A. This is actually step G, for example. And then it puts your output there. So by giving it both the vision in addition to the memory, we've now been able to boost it from low 80% to more 85 to 95% recognition of these things. And the kind of the beauty behind all of this is, yes, it is supervised in terms of we tell it what's going on, but we don't tell it the order that the phase of the operation goes on. You feed it the entire case, you feed it the images, and then it's able to learn on its own the structure and the memory of this. This has led to 80 to 85 to 90% accuracy through a whole wide variety of cases, from lap chole to sleeve gastrectomy to sigmoid colectomy to Roux-en-Y gastric bypass and even an endoscopic procedure poem. And so now we've kind of given it that memory cortex, we've been able to give it that visual cortex, and now we're starting to build upon that fund of knowledge and incorporate all this data and start to move forward. So takeaway points. Really just if you could burn this into your mind and memory, that'd be fantastic. That'd be so nice, just in terms of reading everything. I wish everyone kind of had this. And knowing that what is AI and machine learning? Different, but very much so interconnected and linked, with deep learning being a major kind of type of machine learning that's really been able to help us push this AI field forward. So again, we always just kind of advocate that everyone helps us, what we like to call this collective surgical consciousness, where we need data. That's the current limitation right now. The limitation isn't our algorithms by and large. It's the fact that we need good, really solidly labeled data from a wide variety of patients, wide variety of hospitals, and a wide variety of techniques. So as much as you're able to get those videos, record them, and collaborate with people in your institution, that's kind of our limiting factor right now. It's not the technology, but it's just getting that data and getting people to advocate for it. So please help us do that moving forward. Thank you.